All right, I hope you all are having a restful Thanksgiving break. If you weren't in class the Tuesday before break, we did a lecture on Newton's method, and that's just what this video covers. So let me start with a motivating example. Well, actually, let's call it estimate. Estimate a root of the equation x minus 1 to the fourth equals x squared. Okay, so the whole point of this particular exercise and Newton's method in general is that, sometimes you're looking at an equation that is a bit difficult to solve or perhaps sort of impossible to solve, sort of the same situation we were in the intermediate value theorem section. And we're going to develop a method using linearizations or linear approximations to help estimate roots of equations that we can't solve easily. Okay, although this equation can be most easily solved by sort of taking a positive negative square root of both sides, I'm going to go ahead and expand it out and sort of view it as a fourth degree polynomial equation that we're trying to solve, just to drive home the larger point that fourth degree polynomials in general are not very easy to solve. It's not like we have like a simple quadratic formula or something that we could apply to this. Again, with this particular equation, I could find the roots exactly. They're not going to be nice. They're not even going to be rational numbers. But in general, we're wanting to solve equations something like this. So instead, what I'm going to start investigating the equation, let me go ahead and apply intermediate value theorem to sort of convince myself that there are some roots to this thing. So the standard technique is to create a continuous function. Like this is certainly continuous. It's a polynomial whose roots coincide with the roots of the equation. So any x value that makes f 0 clearly makes this equation satisfied. So f is a continuous function, and if I just start playing around with some numbers that are easy to plug in, so you'll see that these give me some positives and negatives. The intermediate value theorem is going to tell me that anytime this continuous function switches from positive to negative or vice versa, we're guaranteed to have a root in between those x values. So when you plug in 0, you do get 1, which is a positive number. When you plug in 1, you get 0 minus 1, which is a negative number. So I'm guaranteed to have a root in between 0 and 1. So a root somewhere in this interval here. And it just so happens that if you plug the number 4 in, you're going to get 3 to the 4th power minus 9, which is a positive number. And so it's just sort of quick to see that we are guaranteed to have at least 2 roots of this function. One in between 1 and, 0 and 1 I meant to say. Between 0 and 1. Those are the x values that I plugged in. And 1 between 1 and 4. So what Newton's method is going to be, here's the plan, is going to be a better estimation for this root other than just it's somewhere in between 0 and 1. And keep in mind, I could sort of repeatedly apply the intermediate value theorem, like plugging in 1/2 to see whether that's positive or negative, to get a sequence of better approximations of the root. But instead, Newton's method uses a linearization, or a sequence of linearizations rather, to approximate these roots. And we'll see it's just very, very quick in getting a good approximation of our roots a lot of the time. So the plan is first just to give some sort of guess of the value of a root. And right now I have some rough guesses of the values of 2 roots. And then what I'm going to do is apply a sequence of linearizations. So what do I mean by that? I'm going to start with the first linearization of the function, chosen at a good x value, and we'll see that good means, whatever my first guess of the root is. And then that linearization approximates the function and hence gives me a better approximation of the root than my random guess. And I'm going to use that guess in turn to create a new linearization that's going to, better approximate the root, and so on and so forth. So that's the plan for estimating the root. Let me go ahead and show you how it works in this example, and then we'll just develop, what the method is in general. And I'll just warn you right now, like, we're going to develop a formula for estimating the roots of equations, and I want you to sort of resist just memorizing that formula, not thinking about the theory of Newton's method at all. I mean, you're doing calculus when you understand the sequence of linearizations and how they help you approximate a root. Anybody can memorize a formula and apply it. But if you know what the method is and what it's doing, then you're better prepared to not only employ the method, but also like when the method goes wrong, you know what's actually happening. So anyway, let's see how this plays out in this example. My first step here is to make a guess at the value of a root. I'm just going to focus on this root that's in between 0 and 1. So I'm just going to start with a really lazy guess. Let's just say x equals 0 is my first guess. Like I know that, or pardon me, x naught equals 1 is my first guess. I know that that's not a root of the equation because f of 1 is equal to -1. But I want to just show you that, selecting a first guess that's nearby to the root is, most of the time pretty sufficient. So like I know I'm within 1 of the real answer, right? The real root is somewhere in between 0 and 1. I'm just using x equals 1 as a lazy guess. Okay, so here is my first guess, and here is the idea that I'm going to use. Okay, so here's 1, here's 0. The mystery root is somewhere in between. And I know that it exists because the function goes from positive at 0 to negative at 1. Okay, so the function is doing its thing. I'm going to move to Desmos in a second so we can get a view of it, but it's not even entirely necessary right now. The function is doing its thing, okay, and the linearization of the function at x equals 1 is doing its thing, right? So x0 equals 1. And the theory of linearization says that the linearization of the function at x equals 1 should be close to the function, just nearby to x equals 1. Well, hopefully the root is nearby. So whatever my linearization is doing as far as hitting the x-axis should be similar to what my function is doing as far as hitting the x-axis. So let me go ahead and build the linearization of the function at this x value right here, because I understand that this is close to my root and the linearization will be close to my function near the x value which I expand. Okay, so I'm going to make the linearization at 1. So what does that take? Well, I'm going to need to take a derivative, of course. So using chain rule, and then we have this. So the linearization is just the tangent line. Okay, so I've got -2. So I'm finding the slope of the tangent line at x equals 1 and using it to build the equation of the tangent line. So the y value at 1 is -1. And then we've discovered the slope of the tangent line is -2. Here we go. I used point slope form to find the equation of the tangent line. I got -2. I got a +2 minus, so that should be +1. Right, +2 minus 1. Yeah, okay. So this is the equation of my tangent line. So over here, I know that my tangent line is doing something like this. Not very straight, but imagine that this is y equals -2x plus 1. So whatever my function is doing, this tangent line is mimicking it, right? And the further I get away from x equals 1, the further this tangent line is from the function potentially. But again, the idea is if this is close to the root, then the root of the tangent line should be close to the root of the function. So this is basically going to be my next guess at what the root is. Let's go ahead and figure out what that is. Where is the x value that this line crosses the x-axis? Well, that's when the y value equals 0. So if I set my y equal to 0, I see that x equals 1/2. That is going to be my second guess at the root. Okay, so presumably I'm closer to the actual root now, and if I just sort of repeat the process, I can use the following logic. I can say, well, if 1/2 is closer to the root, that means that the linearization at 1/2 is going to be closer to my function near where I need it to be. So I'm going to go ahead and compute the linearization of f at x1 equals 1/2. And so since x1 is closer to the mystery r, the linearization is going to be closer to f, sort of, near the x-axis where I'm trying to figure out where f crosses. So same principle here. I've got my derivative. I now can plug in 1/2 to get the slope. So I have 4 times negative 1/2 cubed minus 2 times 1/2. Let's see what I get. So this is negative 4/8. And here I have minus 1. So this is negative 3/2. That's the slope of the sort of second tangent line that I'm doing right now. And I can build the equation. The y value associated with 1/2, I think I need to figure that out. So let me put that off to the side here. What is f of 1/2? Continue building my tangent line. So the slope was negative 3/2, and then there we go. Okay, so y is 3/2. Okay, so this new linearization does a better job approximating f near my root, assuming that my, new x value that I expanded around, x1 equals 1/2, is closer to the root than my original x value in my original linearization. So the same principle is going to apply here. Now my picture, this method works quickly, so my picture gets like out of date really, really quickly. But anyway, the linearization of the function at this particular x value it's probably going to look something like this. As I said before, I'm going to go to Desmos here in a second, but likely the place at which this new linearization hits the x-axis is even closer to the root r. So let me go ahead and figure out what that number is. So I'm just trying to figure out where this hits the x-axis. So again, I set y equal to 0, and I'm going to get x equals, let's see here, 9/16 times 2/3. So this is 3/8. Okay, and this becomes my new guess at the root, my new and improved guess of the root. So I went from a guess of 1 to, and that was just the sort of very naive guess from intermediate value theorem, to a guess of 1/2 from a first linearization, now to 3/8 from a second linearization. Let's move over to Desmos and see what's actually happening here. So I'm going to go ahead and put in my function f. Okay, there it is, and as you can see, I am getting a root in between 0 and 1 and a root in between 2 and 4, right? Or 1 and 4, right here. And let me put that first tangent line that we found, that first linearization. So the first linearization that I got was negative 2x plus 1. Okay, so as you can see, as expected, the blue line is the function, and the tangent line there at x equals 1 is coming up and it's hitting the x-axis at 1/2. But that's what I guessed. That was my sort of first improvement on the guess of the root. So the true root is somewhere over here, and my first guess is 1/2. Okay, and then my next tangent line, I'm going to have to zoom in so we can see how this works. But my next tangent line, let me find it here, 3/2 x plus 9/16. Picture's already getting cluttered, but let's try and follow this. My sort of improved root was 1/2. And what we did was we computed the linearization at that new x value. That's the purple line here. So it's hard to see, but the purple line is tangent to the blue line, to the blue function right at x equals 1/2. So what's it doing? I mean, it's doing a great job of approximating the function f. As you can see here, it's very close, nearly indistinguishable from f around this region. And hence, since I'm, closer to the root than I was before, this linearization does a great job of approximating the function near the x-axis here. So here's the actual root, here is my approximation, and this right here, 0.375, is 3/8. So what I would do next is I would compute the linearization at this new x value. So I would find the equation of the tangent line right here, and see where it crosses the x-axis. And at that point, I'd be getting a very, very close approximation for what the root is. Let me also show you that Desmos has a Newton's method sort of calculator in it, so you can get a real good visual of what's happening. So let me just use this pre-made thing. So I can just sort of go down and redo the steps that I had done by hand. So here's my function, and if you press this, it'll graph it. Here's my initial guess, and this is going to give me the iterations that come out. So the first iteration, as we see, is the 1/2 approximation. So that's just the image that we were looking at a second ago. The linearization is computed at your first guess, which is this red line. We come up and see where that linearization hits the x-axis, because that's an easy thing to solve, and we get 1/2. That is our new guess. And what we do in the second iteration is we compute the tangent line, or the linearization of the function at that new x value. It's going to even better approximate the function, and our sort of third guess at this point is wherever that tangent line hits the x-axis, in this case 3/8, 0.375. And we can go further. So if we want to do the third iteration, then we expand, or we compute the linearization of the function at 3/8. So it's really even hard to see a distinction between that tangent line and the function. But if you come down here, you can see they slightly diverge. Here's the tangent line, here's the root. So we can see that the tangent line is giving me 0.381928 whatever as an approximation to the actual root, which is sitting right here. So just after 3 iterations, we're getting, the root good to 2 decimal places. Okay, so let's come back to the example here and try and sort of summarize the theory into a formula, which we'll call, Newton's method. All right, so here is our summary. I'm going to summarize the steps that we took and see how it can help us approximate roots, for functions in general. So, we had some function that we knew crossed the x-axis at some mystery point. And our first step was to make some educated guess. Okay, so that's somewhere hopefully close to the root. Okay, then what did we do? We computed the linearization. So what that looks like is, draw the tangent line to the curve at that x value. Let me try and... okay, something like that, and see where it hits the x-axis, and that's going to be your new guess. Well, in general, what does that look like? Well, the equation of the tangent line is the following at x naught, right? And where does that hit the x-axis? Well, when the y is 0, right? So setting y equal to 0 and solving for x, we get that next approximation, okay? So here's our first guess, x naught. I'm wondering what's the x value that makes y 0 in the equation of the tangent line. So I can solve for that, and I get x minus x naught equals negative fx naught over f prime x naught. And I call this x basically my second guess, right? So adding x naught to both sides. This is my improved guess. Okay, and then I go down to the tangent line, or go down to the function, and I make a new linearization. So something like that. Okay, this picture isn't great. Desmos does a better job. But I linearize at x1, and the idea is if x1 is closer to the root than x naught is, this linearization is even better. It's going to even better approximate f near where I need it to. So this right here is my further improved guess, and so on. So I don't need to do this math again. I can see how it's going to play out. x2 is going to be what results from setting the tangent line at x1 equal to 0, and the algebra plays out exactly the same way, so this becomes my third guess. Okay, and so on. You can just keep going and going and going, and the form that you're computing each time looks the same. It basically goes like this. If you have the nth guess, then you can construct the tangent line to the function at that xn value, and plugging in y equals 0 sees where that tangent line hits the x-axis, and that x value, which is expressed like this, is going to be your next guess. So this right here is sort of the formula for Newton's method. Okay, so from now on, if you are using Newton's method to estimate a root, you don't need to go back through the entire construction of the tangent lines and so on to get your guesses. Basically, this formula boils down how the numbers play out when you do that. But I do encourage you to keep that theory in your mind. I really like going to Desmos and seeing the image of the guesses that I'm computing in sequence. Let me also, now that we have the method sort of boxed and everything, let me explore what can go wrong. And you also want to keep that in mind as you're doing your homework examples. So like if you have the picture of what's happening in your mind and something weird happens, you'll know why, because the picture of the tangent lines is going to tell you what's happening with the numbers. So first off, maybe I'll come back to this example since I have it opened in Desmos and say something about the root that this method is detecting for us. So we know it ends up being, something like 0.38 something, right? And the more and more iterations you do, the better approximations you get. You see by the fifth iteration, you're getting it to like 4 or 5 decimal places or something. How would if this method is producing this as the root estimate, how would I use the method to get the other root that I know exists, right? I know that there's another root in between 1 and 4. In fact, the picture made it look like it was in between 2 and 3. How would the method detect that root? Well, it all depends on where you start. So the fact that, let me see if I can zoom out and get the full, actually, let me just go back over here. Turn these off. So here's my function, and the fact that I started with an initial guess of 1 meant the first tangent line that I drew hit the x-axis over here. So that first guess sometimes sort of dictates which root you're going to get close to. So if instead I had selected something, an original guess over in this region, like let's say I, guessed something like 2.5 or something, then coming down to the function, the tangent line, as you can see, would come up and hit the x-axis in between 2 and 3, which would be good. And eventually would settle down to that root instead. So what root you find is highly dependent on where you start, all right? But you can get, both roots of this equation by having a somewhat educated initial guess. Let me consider, for example, what would occur if I chose 2 as my initial guess. Pause the video and think about that for a second. Visually, drawing the tangent line to the function at x equals 2 makes a horizontal line. Now, that linearization does a perfectly good job of estimating the function near x equals 2, right? But it's not going to help us find this root. Why? Because a horizontal line doesn't hit the x-axis, all right? So unfortunately, that's just not a good first guess. That's the method sort of craps out if you choose a bad value like that. So that's going to sort of be our first, how Newton's method, what can go wrong. If our first guess makes the derivative 0, right? That's bad because you can't divide by 0, all right? And we can understand why, again, if we understand the method. So if the root I'm trying to estimate is right here, and my first guess is this, what Newton's method tries to do is use this tangent line and where it hits the x-axis to get a new estimate of the root. That's no good because this tangent line doesn't hit the x-axis. A better first guess would be a little bit closer, and here you go, I'm getting an actual intersection with the tangent line. So that's one possibility. Okay, so consider the following sort of drawing. Okay, I'm going to try and exhibit what can go wrong in a situation like this. Here's our mystery root, and let's say my first guess is somewhere over here. Then Newton's method will draw a tangent line like this. Okay, not great, but imagine that that's the tangent line at that first guess. And then it sends my second guess over here, x1. Okay, and then Newton's method proceeds, draws a tangent line here, and my third guess ends up being out here. As you can see, I've gotten worse with my sequence of guesses, and I don't really have a lot more of the function drawn, so you can see this, but this guess sort of wasn't close enough to the original guess. And depending on the geometry, it may be numerically close, but based on how the slopes are playing out, my guesses might get worse. So if you see your guesses diverging, this might be the geometry that is producing it. And then the last one, it's hard to draw, but let me give it my best. So supposing, again, a similar sort of geometry. Let me try. No, it's going to be, hold on. Okay, if you get yourself into a very particular situation, Newton's method might be producing something like this. So let's say your first guess is here, and the tangent line comes and hits here. Then it might be the case that your second tangent line comes and hits exactly at your original guess. And then that, original guess becomes your third guess. And then you come back, you draw a tangent line there, and your fourth guess is exactly the same as your second guess. And you just end up cycling back and forth between these two x values, and you never hit your actual root right there. So again, if you see this happening numerically, this might be the geometry that is producing it. So what can go wrong is an interesting sort of thing to explore. Keep it in mind when you're doing your problems. And then there are also interesting questions about efficiency, right? I mean, the example that I gave, after 3 or 4 iterations, we are getting a really good approximation of the root. But there are certain characteristics of the function that will either prevent Newton's method from converging to the root quickly, and anyway, that's another sort of interesting thing to keep in mind as you're doing exercises.